All right. Hello and welcome to our um, laboratory assignment and the project for Unit 6, Parallel Communication Patterns. Now, now before we go more into the details of your parallel communication patterns with CUDA, I would like you to just basically write a program, and we will step by step work on this program to see about implementing a map operation. And hopefully this will also help you with if you haven't finished and worked on your Unit 5 assignment. This should give a good deal of explanation and detail on how to use your CUDA as well as your OpenCV to work with images. Now, in this project, what we're going to be using is we're going to use a map operation, and we're going to try to implement the so-called Julius sets. And Julius sets are actually it's an interesting program. It's an interesting calculation that takes into account a set of objects, and it represents the boundary of a certain class of functions on complex numbers. What we have as input for these for our operation is a complex number, and complex numbers are made of two parts, a real part and an imaginary part. And what we do is we pass these numbers into our operation, and then the operation performs a recursive calculation, or rather an iterative calculation, to decide whether or not a point falls within the boundary or within the set. We call it our Julius set, or outside of the Julius set. So if you look at this in a two-dimensional image, each point we can think of the x-axis being the axis of real numbers and the y-axis being the axis of the imaginary numbers. And what we're going to do is that we're going to allocate a number between 0 and 1, or black and white, or 0 and 255 to these numbers. And what that means is that if a number is within the set, it's going to be represented with 1 or 255 or the color white, and if it is outside of our set, it's going to be represented with the number 0. So we're going to write this program, and what we're going to think about is we're going to create a program that has or an image that's a rectangular image, like a 512 by 512. And so in x and y, it'll have 512 pixels in the x and y, 512 pixels in the y dimension. So it's going to be made of 512 times 512 pixels. Then we're going to perform the calculation of the Julius set, which is going to be a two-dimensional for loop that goes through every single pixel. And for each pixel, is going to decide whether that pixel belongs to the Julius set or outside of this boundary of Julius set. And then it colors that pixel. So as you can see, this will be a very interesting project because it has 3 loops associated with it. The loop for x and y to pick a pixel, and then within each pixel, it has to run the Julius set equation, which is going to be a loop. So it's going to be 3 nested loops inside of each other to calculate the Julius set. We're going to implement this set as a CPU process, and then when you see how it's done in the CPU, then we're going to migrate it into our GPU. So the first things first, we're going to set our project up to use CUDA. So we're going to use the CUDA template. Then I'm going to show you how to input and integrate my OpenCV into this project. Then I'm going to take out all the fluff out of my CUDA set project and write my own code. So now I would like you to also follow my steps and do this. So we're going to go and create a new project, and I'm going to go NVIDIA CUDA 5.5 runtime for my example, and I'm going to call it Julia set V100. Then I'm going to take out all of these materials out of my project. All right. Now, if I compile this project, it should work. So there should be no problem. Success. Then, in order for me to be able to see my Julia set, I need to use OpenCV. So how am I going to do this? What I'm going to do is, since I want to add OpenCV, I need to have access to my C++ template. So I'm going to right click on my project and go to add new item, and then I'm going to just add a test.cpp file to my project. I'm not going to add anything to this file. Then I'm going to right click on my project and then go to properties. When the properties window opens up, remember we need to do three steps: add or include libraries, add our or folder, add our library folder and the library files for the OpenCV functionalities we're going to use, and redirect in the debugging section to my DLL folders. So first thing, I'm going to click on CC++, and then I'm going to click on edit, and then when the window pops open, I'm going to add my include libraries. There are two ways to do this. I already have opened up my created a OpenCV dir environment variable and added that to my path. If you've done that, you can use this option, or you can manually type in C:/ the full path to your OpenCV. So I'm going to basically use my OpenCV underscore dir environment variable, and I'm going to use include library there. So OpenCV underscore dir from my environment variable \include. That should add my additional libraries, so I will be able to include my OpenCV header files to my project. Next, I'm going to have to go to my general of the linker, and then on the additional link libraries, click on edit. And then what I have done in my linker, I've added my OpenCV Visual Studio 10 folder into my environment variable as well, and I called it OpenCV underscore dir underscore 32 for the 32-bit version of my Visual Studio 2010, and then from there I'm adding the library folder. So that is if I had added my folder for my Visual Studio 32-bit directories of my binaries from OpenCV. If I haven't done that, you could basically do C:/ the full path, which in my case is gaming programs, OpenCV, build, x86, vc10, lib. Right? But since I already have added all these into an environment variable, I'm just using my environment variable. So no problem in that case. So I added my OpenCV.lib basically to my library path. Then I'm going to have to go and add my linker files, libraries that I'm using. In my case, my library files are version 247. Yours may be a different version, so I'm using OpenCV underscore core 247d.lib and OpenCV underscore high GUI 247d.lib. these 247 is the version of OpenCV that I have. Yours may be 248 or a different version. Notice that I added the entire name with the extension. Since I'm compiling for the debug configuration, I just added the D after my my libraries. So this takes care of my linking process, and the last process is to go and change my working directory to the working directory of OpenCV, because that's where my DLLs are. And so in my case, that directory is called OpenCV underscore dir underscore 32 underscore VC10 /bin. So OpenCV underscore dir underscore 32 underscore VC10 /bin. That adds all my files. Now let's just recompile, although nothing should have changed, and nothing has changed. Alright, so the next order of business is for me to go ahead and create an image and to show it and see if it works. So first off, as you noticed and you have seen before, hopefully, you are going to need to include the OpenCV /cv.h header file, and also include OpenCV /hi GUI.h header file. This will add the functionalities from my OpenCV so that I can program for opening images, working with images, writing images, and things like that. Then what I'm going to do is I'm going to go and add the namespace CV to my project, because the function and the structures and objects that I'm going to use from CV, their namespace is CV, instead of having to type in CV : some object. I'm just including that OpenCV namespace to my project. Now, what I'm going to do right now is I'm going to create an image, and then I'm going to show this image on the screen, right? So in OpenCV, what you the way that an image can be represented is as a matrix of data. And so if you go to OpenCV website, opencv.org, and click on documentation, you'll be able to search through OpenCV library and see how things are structured there. I'm going to click on core functionalities of OpenCV, and it shows you the basic data structures that OpenCV has. And what we need to work with today for this example, because we have an image, is the structure mat. The structure mat is a matrix. It's a data type, and it's essentially it looks like. Let me show you how the structure is created. Okay, so the mat has a bunch of constructors. You can create a matrix by just creating it as an empty object, or creating it as a matrix that has rows, columns, and a type. And the type could be just the size of the data, like for example an 8-byte data, or 24-byte data for RGB, or 32-byte data for 32-bit data for RGBA, and so forth, and a bunch of other things. The parameters that we're interested in are number of rows in a two-dimensional array, because our matrix, our image, is a two-dimensional array, number of columns, again in the two-dimensional array, and the type. The type that I'm going to be using here is CV_8UC1. It's the equivalent of an unsigned character. As you can see here, when it says the data types that OpenCV uses are essentially CV_, and then the size of the data type, 8-bit, 16-bit, 32-bit, 64-bit, and so forth. And then the type of the data type, UC stands for unsigned character. C stands for signed character, or just character. And then number 1 specifies how many bytes you have. So for example, for a black and white image, we basically have 8 bits, or 1 byte. So we're going to use CV_UC1 as our data type. And of course, the data is represented with a pointer, an unsigned char pointer, and that pointer is called data. So these are the three important things that we need to realize. We use a mat structure. We are interested in its number of rows, number of columns, the size of the data that goes into it, the type of the data that goes into it, and the data pointer that points to where the pixels of my image are stored. Okay, so let's get to it. So what I'm going to do is I'm going to create a matrix, and then I'm going to call it my image. And then for this my image, basically what I need to create is a image that has it's a two-dimensional image. So let's just go, and first, before we do that, we're going to define dimensions, and I'm going to make this dimension as a 256 dimensions. So I'm going to create a matrix, call it my image, and size dim, basically 256 columns and 256 rows, CV_8 unsigned char 1. So it's going to create a black and white image, and that image is going to have 256 pixels by 256 pixels, and each pixel is going to be 8 bits. And the 8 bits can range between the color 0 all the way to color 255, which 0 being black and 255 being a white pixel. Now that I have created that, let's see if this image is not created. So I'm going to just do if my image.data is null. If not my image.data, then I'm going to print f something happened and image didn't get created. And else I'm going to show my image in a window. So show basically takes two parameters, a string as the name of the window, doesn't matter what you name it, and then the structure, the input array, which is going to be my image. Then before I exit my program, I'm going to wait. So CV wait key 0. This is going to basically wait for the user to press a key before exiting the program. If you do CV wait key parentheses a number, then that would be the number of milliseconds that a pause is inserted. Let's run this and see if it works. And it did work. So it's going to it shows a 256 by 256 picture image. And as you notice, when I created this, the image I didn't put any numbers, any values to my image. So so the way that it works is that this image is basically a gray image. Essentially, when the image was created with the mat my image, the dimension passed to it. It already is filled with number 127, which is the gray number. Okay, the next order of business for me is to create a structure, basically a abstract data type that will be that I will be able to use to represent complex numbers. So if you remember from your math, your complex numbers are basically numbers that have an imaginary part and a real part. And let me show you how they work. So a complex number can be represented as the length of a vector in 2 dimensions. And so if you have 2 dimensions, x and y, we call them I and j, or r and I rather, real and the imaginary part, then a complex number is represented with a tuple. And I call this C. It's represented with a tuple, R and I. And this is basically the equivalent of R plus I times I, where I is equal to the square root of -1. Okay, so what does this mean is that a complex number that's represented with these two dimensions is going to have a magnitude, and the magnitude of my complex number, or the magnitude C, is going to be R squared plus I squared. Or essentially, it's the norm 2 of this number C. So if you multiply C by C, it's going to be R times R plus -1 squared I times I. There are certain operations that complex numbers support. We will implement two operations here. The operation multiply, that takes two complex numbers and multiplies them, and the operation add, it takes two complex numbers and adds them. Let's say that I have two complex number A, it's made of R sub A and I sub A, and then complex number B, it's made of R sub B and I sub B. If I add A and B, the result is going to be R sub A plus R sub B and I sub A plus I sub B. How does multiplication work? Multiplications work similarly, and if you multiply A and B, then the multiplication is just a little bit more complicated. So what that means is that the real part of the first number, so R sub A, is multiplied by R sub B, and then you subtract from it I sub A times I sub B. That's the real part of the multiplication. The imaginary part of the multiplication is essentially imaginary part of the first multiplied by the real part of the second, plus the imaginary part, the real part of the first multiplied by the imaginary part of the second. So what I'm going to create here is a data structure. And for this data structure, it's going to have two elements, floating point values, R and I for real part and imaginary part. I'm going to create a constructor for it so that I can create objects of complex form. Then I'm going to write a function that calculates the magnitude of a imaginary number, and I'm going to overload the operator plus and the operator multiply for this number to be able to calculate the multiplication and the addition of two complex numbers, because these are the operations that I need to be able to implement my Julia set. So let's get to it. So let's first create our structure. It's really easy to do. So you create struct, and here I call it CPU complex. And my CPU complex will have two variables, or two attributes, or two member values. Float R and float I. R is for its real part, and I is for imaginary part. To be able to create this complex number, I'm going to have to basically create a constructor for it. So I'm going to create a CPU complex. If I pass a float A and a float B, it's going to set the R value as A and the I value as B. So this CPU complex in this format is going to create my constructor. So for example, if I wanted to create a variable of CPU complex type, all I need to do is to type in CPU complex, then the name of the variable, parentheses, its real part, comma, imaginary part, and it's going to create it for me. If I wanted to calculate the magnitude of this of a complex number, I'm going to write a function called float mag2, and the calculation basically is essentially easy. Return the square of the real part plus square of the imaginary part. That's relatively easy. So r times r plus I times I is going to be my magnitude. So this is my creates a complex number, CPU complex number in the form of a comma b, makes it CPU makes it number to be equal to a plus b times I being the square root of -1. The magnitude basically calculates the magnitude of a complex number. So basically the magnitude of C is equal to real squared plus imaginary squared. Okay. Now, then I'm going to overload the two operators, operator multiply and operator add. Let's do the operator add because it's the easiest one. CPU complex, it's going to be the return type of my operator. Operator plus is the operator that I'm overloading, and what's going to pass to it is going to be a constant CPU complex reference to the first number that I'm going to add, and then it's going to return r of my number added with a.r plus I of my number added to a.i. Very easy. If I have oh, sorry, yeah, it needs to return a CPU complex. So CPU complex, so the real part of it is going to be the sum of the two reals, and the imaginary part of it is going to be the sum of the two imaginaries. So if I'm adding a value with another CPU complex A, I'm going to get the I of A and add it to the I of my current number, and the real part of A and add it to the real part of my current number, and then return the whole thing. For calculating the or overloading the operator multiply, again I'm going to pass a CPU complex reference A, and then it's going to return a CPU complex data type. Now this time I'm going to for the real part is going to be the subtraction of the multiplication of real times from the imaginary, and then the imaginary part is going to be real times to the imaginary part of the other ones. So it's going to be r times a dot r minus I times a dot I. That would be the real part of it, and then the imaginary part is going to be I times a dot r plus r times a dot I times a dot r plus r times a times a dot I. So this basically adds two complex numbers, and this multiplies two complex numbers. Okay, so that is my structure, a structure that creates that I can use to create complex numbers. Notice in this example, I'm not using that. I can't use the already native data types like int and so forth. So I had to create my own data type, and this is amazing because I want to show you that you can actually do this. And this is the amazing thing about CUDA programming. It's truly heterogeneous programming. I'm going to migrate these things on my GPU, and my GPU basically will I can tell my GPU that I want you to have these kinds of data structures, and it's going to create those for me later on. So now let's see how I can implement this in or write my Julia set. I said that in Julia set I pass two values, x and y, for the location of my image, and then I'll be able to determine whether that number belongs to my Julia set or falls within the boundary or is outside of my boundary. How am I going to do that? I'm going to basically calculate the values of my Julia set and see whether the magnitude of my Julia set value is greater than or less than 0. To do this, I'm going to create a function, and I'm going to call it Julia. And this function is going to return either a 0 or a 1. 0 if I don't belong to the set, and 1 if I belong to the set. So let's get to that. I'm going to write a function and call it CPU Julia that gets two integers, int x and int y, being the location in my image. I'm going to create a float constant and call it scale, an arbitrary number. I'm going to make it 1.5. Then I'm going to create two float values, a jx and a jy, that it's basically a representation of my x and y, which is the original image, and I want to make the center of the image to be 0, 0, and then when I go to the right and the left and the up and down, to go dim over 2, dim over 2, dim over 2, dim over 2, dim being the dimension of my image. So I'm going to create float jx being equal to scale times, I'm going to cast dim over 2 minus x over dim over 2. So that is going to create from my original x value and y value, I'm going to create a new x and y value in which the center of my image is going to be 0.0, 0, and then as I go to the right or the left or up or down, I'm going to go from 0 to dim over 2 and 0 to negative dim over 2 in either directions. Okay, then from this point I'm going to create two complex number, a CPU complex made of my j sub x and j sub y for my image number, and then an arbitrary complex number that's the representation, actually let's call this a, and the representation of some arbitrary number such as 0.8 and 0.156. This is basically, you can think of it as a steering of my Julia set. So this will be a control point. So a, the complex number a based off of j sub x and j sub y, is going to be a complex number off of my image, location of my each pixel in the image, and then c is a control point, and it's an arbitrary number that I can use within the calculation of the Julia set. And the equations of the Julia set are in your textbook, or you can search them online and learn about how these are implemented. Then as I said, I need a Julia set calculation runs an iterative process. And for example, in this case, I'm going to run it 200 times. And then each time I'm going to calculate, I'm going to multiply a by itself and add the control value to it and store it into A. And I keep doing this until the magnitude of A is greater than some constant time. And if it is, then it's outside of the boundary. If not, it's inside of the boundary. So I'm going to create the index 0 and make it for like 200 iterations. And within this 200 iterations, I'm going to run my Julia set calculation. So Julia set calculation is going to be A square of A plus C. So I do this calculation for 200 times, and if the magnitude of A is greater than, say, 1000, then it's going to be outside of my boundary, so I'm going to return 0. Otherwise, if I run these 200 iterations and the magnitude of A is still less than 1000, then I'm going to return 1. Okay, so line number 39 to 58 is the calculation of my Julia value being 0 or 1. 1 if my pixel belongs to the Julia set, 0 if it falls outside of Julia set. How do I do the calculation? I create a scale pointer, a scale value. I reformat my image, which is 0 to 512 or 0 to dim in x and y dimensions, so that the center of the image is 0, 0. Then I'm going to create a complex number for each pixel and a complex control value. Then I'm going to run my Julia calculation 200 times, and this line, line 52, this is the calculation of Julia function for pixel A, Jx and Jy, and C, and basically the control value. And then here, if the magnitude of Julia function for A is more than 1000, then the pixel is outside of set. Otherwise, pixel is inside Julia set. Wonderful. So now I've written my Julia function to take a pixel value and return 0 or 1 depending whether or not it belongs to the Julia set or not. So now my final function is to write a function, and I'm going to call this CPU kernel because it runs on the CPU, and have this function to go from 0 to dim on x and y for rows and columns of my image, and then decide whether or not that pixel is in or outside of the Julia set. And if it's inside of the Julia set, then I'm going to basically calculate that value, their Julia value, as the color of that pixel. So I'm going to write a void kernel, and I call it CPU kernel. And this CPU kernel is going to take a use unsigned char pointer as my CPU data, basically the data of my my image, and then assign the color to that data point. So I have two for loops: a for int y equals 0, y less than dim y plus plus, for int x equals 0, x less than dim, remember dim is the dimension of my image, x plus plus. And then inside of there, I'm going to calculate an offset. Remember, when you have a two-dimensional object or a two-dimensional image, you have x and y. But data of your matrix pointer is a one-dimensional data. So I need to map my two-dimensional x and y into a one-dimensional location for that pixel. And it's really easy. The offset since my data is in an X major, it's going to be equal to X plus Y times dim. So once my offset is calculated, I'm going to calculate int Julia value equals CPU Julia of X and Y. And then the Julia value is going to be 0 or 1, depending whether X and Y pixel is inside, or rather outside or inside of my Julia set. And then I'm going to use the Julia value as the color of my pixel. So my CPU data at location of set is going to be 255 times Julia value. Okay, so now again, let's run this function. So for each column and for each row, find location of pixel in data. Let's call it mat.data. And then calculate Julia value for pixel X and Y, and then assign color of Julia value to pixel X and Y, which is in location offset in your data pointer, okay, in your CPU data. Now, one last thing is left for me to do, and that is here. When I created my image, create an image, call it my image with size dim, comma dim, right? When I created my image, now I need to pass the data pointer of this image to CPU kernel to be able to paint this image. And that is going to be incredibly simple. All I need to do is to call CPU kernel and then pass to this kernel my image.data. This calculates the image color per Julia set. Now, there's one last thing that I need to do actually. I need to do this within this else loop, right? Because if something goes wrong and my CPU data or my image data is not created, then my program will break. So I migrated this CPU kernel call on my image data if the image was actually created. Now, I haven't compiled this step by step, which is a big mistake. So I want you all, when you're writing this program, for every single line or a few lines you write, compile it so that you won't get any errors. So I'm going to compile this, and if it actually compiles, it's going to be a miracle. But bear with me. So it did compile. Let's run it. And voila! That is the Julia set that is created here with a 256 by 256 image. Let's make this a little bigger, and let's change the dim from 256 to like 680. And this is my Julia set run on CPU for 680 by 680 image. And as you see, the pixels that are white are the ones that belong to the Julia set, and the ones that are black are outside of the Julia set. So there are certain control parameters that I can control. For example, the scale, I use 1.5. What if I make it 5? It's going to give you a coarser or a smaller scale of this Julia set. And if I do 0.5, it's going to be magnified. So that's going to be the scale of my operation, right? So here I'm kind of sort of magnified into my image. And okay, so this is the Julia set calculation, and this looks pretty good. Now next we're going to migrate this onto GPU. And notice that this is actually a map operation. I'm going to go for every pixel, and this is a kernel. I'm going to go for every pixel. I calculate an offset, calculate the Julia value, and write it into the offset. So every pixel will associate a 1-to-1 mapping between my input data and my output data.